to understand the expression for the ripple factor, we need to know this all thing which we have already covered, but let's go very briefly, or in short duration I will recall. So we know, if we consider the rectifier, we are converting AC into DC. So we know actually the output of rectifier is not pure DC, we get the pulsating DC. So this may be the output if we are talking about the full wave rectifier, in which you can see the output is not pure DC but it's a pulsating DC. And to get the pure DC, what we do, we further connect a filter at the output of the rectifier. So the filter may be anything. Normally we connect a capacitor or we connect a inductor here. So let us consider a capacitor filter. So if this is the circuit, this is called as the filter, which is connected at the output of the rectifier to smooth out these waveforms. After connecting the filter, the waveforms are now modified. We know, from this to this, the capacitor starts charging. After charging to this maximum potential, which is normally equal to potential called Vm, right? After charging to the maximum potential, as this voltage is decreasing, so capacitor has to discharge through this resistor, but the resistor is having high value, that's why capacitor will take more time to discharge. So that's why the capacitor discharges very slowly like this. After discharging, when this time interval come, again the capacitor starts charging because the voltage is rising, that's why it will again start charging and the voltage across capacitor increases up to the maximum value, which is Vm. After this, again the input means this voltage is decreasing, so capacitor has to discharge, so it will again discharge, and discharging time is, again we know why it is higher, and this cycle will go on continuously. In this way we are getting this waveform at the output of, means at the output when the filter is connected. Now in this study we are interested in this waveform only, which we are getting after connecting the filter. So I will suggest minor modifications here. Let us see what are the modifications. First of all, I have marked the maximum and minimum values of this waveform which I am getting, and I am considering that this is equal to VR, which is the output I am getting after connecting the filter, right? So this is, we can call as the output voltage. And another modification I am suggesting is that here I am considering the capacitor is, means the output waveforms I am getting in a steady state, so I will take this waveform to be smooth out like this. So this I am considering as a steady state waveform. So this is the final waveform which we are considering, which is available at the output of the rectifier after connecting the filter. As we know, this is the half cycle, and that's why this total time duration can be called as T divided by 2. It is a half cycle, that's why it is T divided by 2. Another, let us consider that this time during which the capacitor is charging, you can consider here or in the this cycle also, anywhere you can consider as per your comfort. So this time in which the capacitor is charging, let us call it as a T1, and the time this from this to this where the capacitor is discharging, let us consider as a time T2. So in this way, time T1 and T2 are making one half cycle, which is equal to time T by 2 if we do the comparison. Now as I said, I am interested in this waveform only, so I will zoom out this particular portion. I will draw it once again here. Before that, another assumption which I am making is, let us consider these lines as a straight lines like this. Let us assume that these are the straight lines. So these are actually making the equivalent to the triangular waveforms. So I will draw the triangular waveform here. So here you can see these are the waveforms which I tried to draw. Just what I did is I have zoomed out this particular portion. Now again let us write the same notations here. As we know, this is the portion in which the capacitor is charging, and we should be careful, and we should indicate it very correctly that the charging time for the capacitor is very small as compared to the discharging time. So as we have given the notation, the charging time is given by time interval t1 and discharging time is given by time interval t2, and the total sum of t1 and t2 is nothing but the half cycle. So that's why it is nothing but a t by 2. The same notations which I have done here, I have taken as they are. Another thing is that, as we know, this value, peak to peak value of this waveform is called VR, and that's why I will write the same thing here. This peak to peak value is nothing but the VR. So these waveforms I am calling as a triangular approximation of ripple voltage. So this ripple voltage I have approximated in terms of the triangular waveform. And now if you understood this thing, we are actually interested in finding out the equation for this waveform. So now here onwards I am going to consider this waveform and removing all these things. So we are going to consider this waveform here. As we know, this is peak to peak VR, so that's why it will be VR by 2. Another thing is that we are going to use the new equation for ripple factor, which I will be writing like VRMS divided by EDC. Now from where this equation came, I will explain on the another slide. Actually, we have derived this equation earlier. RMS, the ripple factor is given by this equation, under root in bracket RMS, IRMS divided by IDC bracket square minus 1. But here we will use the voltages instead of current. So that's why first of all this voltage currents will be replaced by voltage. So here what I can write is, instead of IRMS I am writing VRMS, instead of IDC I am writing EDC, and this expression. Another thing is that to make this simple, what I will do, I will neglect this 1. So if the 1 is neglected, then I am remaining with only VRMS divided by EDC and bracket its square. Further, now you can understand, after solving this I am getting it equal to VRMS divided by EDC. So that is what equation I have written here. Now if I get the equation for this VRMS for this waveform, I will be getting the ripple factor. I will use the standard equation now. The RMS value of the triangular waveform is given by this formula, VRMS equal to VR divided by 2 under root 3, where VR is indicating this peak to peak value of the triangular waveform. Thus it means that in order to find out the equation for VRMS, I need to find the equation for this VR. Now we know that the capacitor is charging during time t1 and it is discharging during time t2. So it means that it is accumulating the charge during t1 and it is losing its stored charge during time t2. So during T2 capacitor discharges and we will use the equation which is indicating the charge lost, which is given by the basic equation of charge, that is Q is equal to C into VR. So this is the equation for the charge which the capacitor will lose. But we also have one equation for the current which is flowing through the circuit. Like in terms of charge, we can write I is equal to dq by dt. That is the general equation for the charge, which is given by I is equal to dq by dt. So further from this equation, what I can write the equation for this charge q as q is equal to, now it is the derivation, so here I will take the integration, so like this. So from this expression actually I am getting the equation for charge q. So it is charge q is equal to integration of I dt. And now here we are talking this during the discharge time, means during the time interval t2. That's why the limits will be from 0 to time t2. This is time t2. Okay. So further this can be written like IDC, means average current which is flowing during the time t2 only. So that's why I will be writing Q is equal to IDC into time interval T2. So here actually what I did is I have got the two equations for the charge Q, which is getting loose during the time interval T2. So this is one expression for Q. This is the another expression for Q. It means this term is comparable with the term IDC into T2. So same thing I'm going to write here. So now I will write here. I have the expression like IDC into time T2 is equal to C into VR, right? So now let us find out the equation for VR. Actually, all this we have started from here where we were interested in finding the value of VR. So here we got the value VR is equal to, from this expression, it is IDC multiplied by time T2 divided by capacitor C. So this I am taking as a equation number 1. Now let us simplify this further. What we can write, looking to this diagram, what we can write is the total time, that is T by 2, is nothing but equal to T1 plus T2. But the thing is that here T1 is the charging time of capacitor, which is almost very small. So that's why T1 is very small as compared to T2. That's why what I will do, I will neglect this term T1, and that's why this T by 2 is actually coming to be nearly equal to T2. So it means that in this expression where I have T2, it can be replaced by T by 2 here. So that's why I will write the new equation for the VR, which is coming to be VR is equal to IDC divided by C, and instead of T2 I will write T by 2. The explanation is here. So it is T by 2. Further we know that what is this T? T is nothing but the time period of this waveform. So time period is nothing but the 1 divided by frequency. So what I can write is, I can write the equation for this VR is equal to IDC divided by 2, this 2, and FC. So instead of this T, I have written F here. The reason you should be knowing that the time interval T is nothing but 1 by frequency. So instead of taking the time, I have taken the frequency here. So finally, I have got the equation VR is equal to IDC divided by 2 into FC. Now let us again take the equation in terms of voltage, not in terms of current. So I will replace this IDC by voltage value. So what I can write is IDC is nothing but EDC divided by RL. So if I put IDC is equal to EDC by RL in this expression, so I will be getting the equation for VR is equal to here EDC divided by 2 into F into C into RL. So this is how I have got the equation for VR. Why I gone for this equation? Because VR was requiring for calculating the RMS value of the triangular waveform. So in this way I have got the the RMS value of this triangular waveform, which is VR divided by 2 root 3. So if I put this VR here, I will be getting the RMS value of the triangular waveform. So that's why here I will write to save the space. So in this way, VRMS, this VR I am putting here. So it is coming to be simple EDC divided by this 2, and this 2 will make it 4, this under root 3 as it is, and F into C into RL. So F into C into RL. So this is how I have got the equation for the VRMS for this triangular waveform. So after this, almost it is done. What we have to do is we have to get this equation of ripple factor by putting the VRMS here. So now the ripple factor equation. So I will write ripple factor. Now this is the case of full wave rectifier. So ripple factor here is, as we know, it is expression Vrms divided by EDC. This expression I have written in the very starting and I explained you how it came. So I will put the Vrms, this expression here, and I will be getting the final value. So this is EDC divided by 4 under root 3 F into C into RL, and this EDC as it is, so 1 divided by EDC. Now simply you can see this EDC will get cancelled, and I am getting the final equation for the ripple factor in case of this full wave rectifier. I will write ripple factor in full wave rectifier is equal to this EDC will get cancelled. So I am remaining with 4 under root 3 into F into C into RL. This is the expression for the ripple factor in case of full wave rectifier. So if we have got the equation for ripple factor in case of full wave rectifier, similarly we can go for ripple factor in half wave rectifier, and as we know, normally they are correlated. So we know in case of full wave rectifier ripple factor is more. So if this term is multiplied by 2, we'll be getting the ripple factor of half wave rectifier. So that's why I can write the ripple factor in case of half wave rectifier is this expression multiplied by 2. So I will be getting, after solving completely, 1 divided by under root 3 F into C into RL. So that is the expression for the ripple factor in case of half wave rectifier. If you want, you can derive the same. Ultimately, the conclusion is that if you want to reduce the ripple factor, what you have to do is you can increase the value of this capacitor, or you can increase the value of this capacitor, or you can increase the value of this load resistor. So to reduce ripple factor, you increase either capacitor, or you increase load, or you increase both. So this is how we can justify the ripple factor can be reduced by increasing the value of capacitor or increasing the value of the load resistor.